Hi, I'm Nikki from educatingnow.com. Thank you for joining us while we explore the partial quotient method for long division. This is also sometimes called the repeated subtraction method. The goals for this lesson are for students firstly to be able to understand how and why the partial quotient method of division works, as well as to use specific mathematical language to explain the steps that they use in order to solve division questions using the partial quotient method. I find this method extremely valuable for those students who have yet to remember or understand the traditional long division algorithm. The traditional algorithm is one of the most misunderstood and misused algorithms and the most forgotten algorithm out there. So this method often gives students a chance, especially if they are in grade 7 or 8 and have already been taught the traditional method several years in a row and still don't understand it or still can't use it or haven't really memorized how to use it. This method gives them a chance to be successful at division. I also believe that this method builds number sense in a greater capacity than the traditional algorithm, so it is actually my preferred method. It also can be used with decimal division as well, so it is not limited to just whole number division. For the accessing prior knowledge part of this lesson sequence, I would ask my students to get into partners and discuss what is division. I want them to really understand what division means. Whether they are thinking about it as equal sharing or equal grouping, we want them to understand the concept. I would then ask my students to show me 21 divided by 7 by using repeated subtraction. So just as multiplication is repeated addition, division can also be thought of as repeated subtraction. So when we look at an example like 21 divided by 7, what we are saying is how many groups of 7 can I take away from 21? And of course the answer is 3. Because students will need to be able to multiply by multiples of 10. So for example, in order to be successful at this method, students will need to understand how to multiply things like 7 times 30. So if you haven't already done some practice multiplying by numbers this large, now would be a good time to do that before you get into using the partial quotient method, as it relies very heavily on their ability to multiply. For the processing part of this lesson sequence, we're going to be looking at what this partial quotient method really means. So it does require students to think about how many groups of the divisor we can take away from the dividend. So in this case, we're going to take a look at 381 divided by 6. So we want to think about either how many groups of 6 can we take away from 381, which would be an example of equal grouping. Or we can think about it as we're taking 381 and dividing it into 6 equal-sized groups. How much can we put into each group? I do find that some of my most struggling learners like to use what I call bubbles, or simple drawings of circles with the amount that they group into each. The first thing I ask my students to do, no matter what the question is to estimate. I find that this estimation actually helps them to get started using the partial quotient method, so it serves a very useful purpose. So here we would think about how many groups of 6 can I make out of 381. I know that 60 groups of 6 would give me 360, so I know that my answer is going to be a little bit bigger than 60. Let's take a look at the partial quotient method symbolically and pictorially. I am going to use just simple circles to represent my 6 equal groups, and I am just going to use numbers, symbols, in each of the groups. If you choose, you can do a true pictorial representation by actually drawing the base 10 blocks into each of these bubbles. The age and the skill level of my student would depend on whether or not I use the actual base 10 blocks. If I'm working with grade 7 or 8 students, I will stick with the symbolic, as most of them are able to at least conceptualize what we're doing here by using the bubbles. If I was working on this method with students in grades 3, 4, 5, and perhaps 6, I would probably use the base 10 blocks, or at least pictures of. So let's take a look here. If we start with 381, and we are going to be dividing that into 6 equal size groups, how much can we put in each group? We want to encourage our students to use easy to use numbers. So we don't want them to choose things like 53 or 54, but 50 would be a great starting point. Many of my students like working with 50 because it's half of 100, and they would know that 6 groups of 100 is 600, which is far too big. So they can half that and see that 6 groups of 50 would actually give me 300, which works well for this problem. So I'm recording both in my bubbles and in my algorithm here that I have now subtracted or divvied out 50 into 6 groups, which means I have divvied out or taken away 300 from my 381 that I've started with, which leaves me with 81. Now, again, students can choose any number they want as long as the product doesn't go above 81. Many of my students would probably choose 10 because they know that 6 groups of 10 is 60, and that's pretty close to 81. Once we record that, we can see that that has divvied or taken away 60 from the 81, which leaves me with 21. Now I'm working with much smaller numbers, and so it's far easier for me to see where I go from here. I can now put 3 into each of my 6 groups, which would take away another 18, and I am only left with a remainder of 3, which means I am almost finished. Now I just take a look at how much I put into each group. I can see that I put 50, 10, and 3, so a total of 63, and I have 3 divided into 6 groups, so that would be 3/6 in each group, or if you'd like to reduce that to 1/2. I also really like this method for showing students how we write our remainder as a fraction, because it's really clear, especially with the bubbles on the side, to see that we are taking our last 3 and dividing it or splitting it into 6 equal groups. So that would only be 1/2 into each group. Let's take a look at another example. My next example, I'm going to use a larger number. I'm going to take 4,295 and divide it into 8 equal size groups. First, we're going to start with an estimate. I know that 1,000 groups of 8 or 8 groups of 1,000 would give me 8,000. And I can see here that I have a little bit more than half of that. So I'm going to start with 500, and that's going to be my estimate. I know it's going to be a little bit bigger than 500, but it also gives me my jumping off point. So I'm going to start by putting 500 into each of my 8 groups. And by using this halving strategy, students can easily determine that 8 groups of 500 is 4,000. Alternately, they could look at it as multiplication. 8 times 500 would be, you could think about it as 8 groups of 5, which is 40, but now we have to make it 100 times bigger, which brings us to 4,000. So I have now taken away 4,000 from my 4,295, which leaves me with 295. Now, again, using multiplication and working up, I know that 8 groups of 3 is 24, therefore 8 groups of 30 is 10 times that, so 240, which brings me pretty close to 295. So I'm going to put 30 in each group. One of the things I love about this method is that students can choose so many different numbers to put into their groups, depending on which multiplication facts they know or which numbers immediately jump into mind. I do find that as I practice this method often, the students get a lot better at picking the biggest possible number to get to the answer very quickly. I also find that this is a method I almost never have to reteach or remind students how to do it, which is very different from the traditional algorithm where my students forget it within a month or 2, if not every single year. They have completely forgotten how to do their long division. This method often makes so much more sense to them that they have no problems at all remembering it. And I find some students way prefer this method even when working with division of decimals, which I find quite challenging, but many of them find it far simpler to use this method for all their division needs rather than the long division algorithm at all. So coming back to our problem here, we've now subtracted 240 from our 295, which leaves us with 55. And I know that I can put 6 into each of my groups, which would take care of 48. And when I subtract 48 from my 55, I'm left with a remainder of 7. So altogether, I put 536 into each of my groups, and I have a remainder of 7 divided amongst 8 groups, or 7/8. I suggest doing several more examples and then having your students come up to the board and showing their methods, as each student could do this in a different way and still get the correct answer. This could lead to a class discussion around the merits of each example, such as whose was the fastest, who used the easiest numbers, etc. For the transforming part of this lesson sequence, you have a number of choices. You can give your students some open tasks, such as 2 numbers have been divided and the answer is 452. What could those 2 numbers be? Or you could just give your students some division questions and ask them to solve them using the partial quotient method. I like to have my students mark each other's work for this because there are so many different ways in which they could choose the different groups that they decide to take away. There are a multitude of different answers that are all correct, that I think is interesting for students to see how other students chose their numbers, because they might see some strategies that will help them out when they continue to use this in the future. For the reflection part of this lesson sequence, I ask my students what they found the easiest and most challenging aspects of using this method of division. I also ask them whether or not they prefer this method of division or the traditional algorithm, and why. Thank you for joining us at educatingnow.com while we explored the partial quotient method of division.